This is my submission for Chapter 29 exam. Part A states a single circular loop of wire with radius 2.40 centimeters lies in the XY plane. There is a uniform magnetic field that changes at a steady rate from 0.140 T in the positive Z direction at T equals 0 to 0.110 T in the negative Z direction at T equals 2 seconds. Take the area vector for the loop to be in the positive Z direction. Find the magnetic flux through the loop at T equals 0. So for this, we're going to use the following formula. Pi, just basically we're just finding the area and multiplying that by the magnetic field. So it would be pi times r squared times our magnetic field. This is equal to pi times 2.40 times 10 to the negative 2 power squared times our magnetic field 0.140, because we're looking for B1, and this is equal to 2.53 times 10 to the negative 4, and then our units, Webers. Part B is asking us to find the magnetic flux through the loop at 2 seconds. For this, we're gonna use the same formula, but we're not gonna use the same formula, we're gonna multiply the magnetic field times the area. But what's our area? Basically, it's this, pi times 2.40 times 10 to the negative 2 power squared, and this is equal to 0.0018 meters squared. And now we're gonna multiply that 0.0018 times our magnetic field, or B2, which is 0.110, and we get negative 1.99 times 10 to the negative 4th power Webers. For part C, we're asked to find the magnitude of the induced EMF in the loop while the field is charging. So for this, we're gonna use this formula for the EMF, minus the second divided by, okay, so here we're gonna use our first value that we found, the 2.53 times 10 to the negative 4. We're gonna subtract it by the second value that we found, 1.99 times 10 to the negative 4, and we're gonna divide this by 2. Just writing this down so we can see the signs correctly. And then all of this is equal to 2.26 times 10 to the negative 4 volts. Part D is asking a circular coil with 455 turns of wire has a radius of 5 centimeters and resistance of 14.5 ohms. The area vector of the coil points in the positive Z direction. The coil is in a region of uniform magnetic field that points 20 degrees from the positive Z direction. The magnitude of the field is initially at 0.0600 T and decreases at a rate of negative 3 times 10 to the negative 3 T per second. Find the magnitude of the induced EMF. So here we're going to use the following formula for EMF. Is a negative derivative of this divided by dt. Okay, so then let's just solve this a little bit. This would be negative d divided by dt, and BA, because we're using that formula, cosine of theta. And then all of this is equal to negative n a cosine of theta dB over dt. And now we plug our given values. This would be negative 455 times pi times 0.05 squared cosine of 20 degrees multiplied by 3 times 10 to the negative 3. And all of this is equal to 10.069 times 10 to the negative third power, or we can also say that this is equal to 1.01 times 10 to the negative 2 volts. Okay, part E is asking to find the magnitude of the induced current in the coil while the field is charging. For this, we're going to use the following formula. I is equal to divided by R. This is equal to what we just found, 1.1 times 10 to the negative 2, and then the resistance that was given to us at the beginning of the problem, 14.2, and this is equal to 0.0696 times 10 to the negative 2 power, or we can also say that this is equal to 6.96 times 10 to the negative 4th power amperes for our current. Part F states a square single loop of wire 4 centimeters on a side with 875 turns lies in the XY plane. The loop is in a uniform magnetic field that changes at a steady rate from vector B 0.200 Ti plus 0.150 Tj at T equals 0 to vector B is equal to 0.300 Ti plus negative 0.200 Tk at 3 seconds. At the time 2 seconds, find the magnitude of the induced EMF in the coil. So for this, we're going to use the following formula for the EMF. This is theta, but we're going to use the other one, divided by dt. And this is equal to, we're going to plug our values in, 875 times 0.04 squared times 0.2 plus 0.15, all of the stuff that we were given. And all of this is going to be divided by 3. And this is equal to 0.163 volts. Part G is asking us to find the direction of the induced current in the coil as seen from a point on the positive z-axis. So the direction of the current in this case is counterclockwise, so that would be our answer. Part H, a coil with area N, A and N, turns of wire lines, a coil with area A and N, turns of wire lies in the XY plane. Its area vector points in the positive z direction. It is exposed to a uniform time variant magnetic field. Vector b is equal to b of 0 sine wt k, vector k, where w is a positive constant. Find the included ELM in the coil. Okay, so the flux through a coil is given by the following formula, and vector b times vector a. For the magnetic vector, which we were given, and the area vector of a coil, which is vector a, is equal to our area times vector k. We find that the flux through the coil is given by this, and then solving a little bit, we get n times b of 0 times our area times sine of wt. And then an m through a coil, we know it's the negative derivative of d in this divided by dt. So plugging these things together, moving them together, gives us negative n times b of 0 times a times the derivative of d, divided by dt. So d divided by dt, times sine wt. So we're going to find the derivative here. And then when we do, we get negative n times b of 0 times a w cosine of wt. And that is our answer for part H. And then part I is asking us to find the direction of the induced current in the coil as seen from a point on the positive z-axis and t equals 0, and add t is equal to pi divided by w. So when we use for this problem, the two ways that we can approach it, we can use the right hand rule to help guide us in the direction, or we can also use Lenz's law, which states that induced currents direction must be opposite to the magnetic flux it's creating. So in this case, it would be clockwise at t equals 0 and counterclockwise at t is equal to pi divided by w. Because at t equals 0, it's increasing in the positive z direction, so the induced current is in the clockwise direction to oppose the flux increase. And at t is equal to pi divided by w, b equals 0, it's increasing in the negative z direction, so the induced current is counterclockwise to oppose the flux increase. I'm not writing that down because it's a little bit easier to explain with words, but that would be the answer for part I. Again, this is my submission, Victoria Tencio, for exam chapter 29. Thank you.